love the
I like
mechanical.
I like mechanical watches, but I do an Apple Watch. But a friend of mine talked to me. He was like, "Well, what do you?" Yeah, I've had that question so many times when I've talked to people about like kind of watchmaking.
Yeah,
They are two different things. Like I don't even put the only thing that's the same about an Apple Watch and a mechanical watch is that they fit on the same part of your body.
they've
That's
got
it.
a wristband.
They got a wristband. It's a totally different device, right? I
Yeah,
mean, like an Apple Watch, it's like, yeah, I use it for working out. I use it for, times like, um, yeah, mostly it's like for exercise, kind of track progress. Sometimes I
sure.
use it like when I'm driving, like so I can use like Siri and stuff like that.
Oh
And
yeah,
like so
yeah,
it's a totally different device. But I do have one and I like it. It's great for certain things. But
yeah.
yeah, like I said, it's a totally different device. How about you? Do you run an Apple Watch or any sort
So
of
yeah, I definitely
wearable?
have an Apple Watch, and I probably don't use it nearly to the extent of what it can do, but kind of the same thing. It's just like it's super nice just to have the notification show up, like if I'm
Hmm.
getting a phone call and my phone is somewhere else or whatever. So I just kind of use it for that. But there is something like really satisfying about a real watch, like just the feel of it on your wrist and the mechanical nature of it. It's just very satisfying. My wife had gotten me a not a super fancy one, but like as a wedding gift had gotten me a watch, and it's I don't know. There's like there's something just very like personal about it, like where there's not so much with like an Apple Watch necessarily. Obviously they're nice and whatnot, but yeah, there's kind of a personality to a real watch. That's
I
interesting.
I totally agree. And it's like this like little living organism on your hand, right? It's not connected to anything. It's a very simple device of like gears and springs, and that's about
Yeah,
it. You
yeah.
know, uh, yeah, it's like a little car engine connected to your wrist. I love it.
Did
And
you?
mhm.
I was gonna say, did you how where were you like a mechanical watch wearer and then you got into it, or did like getting into it and really starting to understand the mechanics of it want you to start wearing one more?
Yeah, the latter. I've never been a watch wearer. I
Ah,
wore a watch before I had a phone. I wore a watch as
okay.
that so I could know what time it was. Once I got a phone, literally that watch, I was like the first person on the planet to get rid of the wristwatch. I don't like jewelry. I don't like things on me. I mean, like if you look, like this is about as much jewelry as I can do.
Yeah,
Like
yeah,
this, it's like it's a gold wire. It's about as small as you could possibly get. That's all I can do. I'm not a jewelry person. I don't like
yeah.
things like connected to my body. But yeah, I just kind of started kind of getting into watches just from like I was just like watching videos. I mean, the real way it came about is I was watching these like restoration videos that we've all probably seen a million times on YouTube, where
Yeah.
like someone takes like an old bench vise, let's just say, and then they tear it down, they derust it, they sandblast it, right? They fill all the gaps, they then paint it and put it back together and it's like brand new. And then,
Yeah.
YouTube's going to suggest all kinds of videos
Right.
based on what, and I was like, oh, a wristwatch, someone rebuilding a Rolex. It's like,
Yeah.
sure, let's see what that's about. And I was like, oh, like, this is really interesting.
Well, and it's funny too, because you kind of get in those rabbit holes, and suddenly something that didn't seem like that you would normally have felt like you could do at all, you're suddenly like, I can do this.
Yeah, yeah, no, for reals. Yeah, just like caulking is something that I always feel like I can do when I watch a video, and then I actually try to caulk something, and I get
Well, yeah.
caulking everywhere, and it's an
Right.
absolute huge mess. So I am like literally the world's worst with a caulking gun. The worst. I am the
Yeah.
worst.
Me too.
I'll take on anybody as the worst person in the world who does caulking in like a bathroom or kitchen.
I get it.
It's
I always have it all over the place by the
all
time
over the place.
it's
It's everywhere.
ridiculous.
It's on my
What it?
hand, like my kitchen. Like I recently had to recalk my kitchen sink,
Yeah.
and I swear, like even today, like there's like bits of caulking on all the tile around it, and I'm just like, I see when I'm just like my fingernails like just like scraping. Oh, it's the worst.
Yeah.
Yeah, YouTube doesn't do everything for you.
Speaking of YouTube though, it's interesting. I don't know if it's just because you know I had searched on something or what, but I in my feed it came up a guy talking about, ironically, Rolex watch.
Hmm,
Back to the topic of watches, he was talking about
yeah.
Rolexes and how they're actually a non-for-profit.
What?
Yeah, if you Google it, Rolex is owned by a the foundation, the guy that originally built the watch, started a foundation, and 100% of Rolex is owned by the foundation. And so they're effectively a non-for-profit, which is just crazy to think about.
That is crazy to think about. It just, I immediately think, oh, it's a tax shelter. But like there's some way they're using that to game the system, but maybe
Right.
not. I mean, Rolex is like, I've never been like a Rolex fan because I'm not into like gaudy stuff.
Yeah.
But you have to respect Rolex as a brand because they have never made a watch that takes a battery ever.
Right.
Like they are 100% mechanical from day one to today. They've never kind of, you could say, moved to the dark side. Every other watch company at least has a line of quartz watches. Rolex never did it.
Right. Well, hey, let's speaking of watches, let's kick things off. Big shout out to everybody that is in the chat with us this morning, this afternoon, wherever you're joining from. My name is Steve Fick. I'm happy to be hosting today a great colleague of mine, Andrew Gross, who's going to be taking us through a hobby of his that has become quite interesting. Andrew, I remember the first time you brought this up in one of our team meetings. I was like, wait, what? You're doing what?
Well, so I mean, I think like everyone, like all hobbies that we have, we don't think like, I think I'm going to get into a new hobby. It's like usually it's something that just happens like without you thinking about it, because you get excited about something. You're like, oh, I didn't know about that, or I didn't. That sounds pretty cool. A lot of times it's kind of spontaneous, the hobbies that we get into, right?
Well, and like all of us are like, well, at least for me and you, I think our hobbies suddenly end up in SolidWorks, right? It's like, oh, I can do this in SolidWorks.
I literally don't have a single hobby that hasn't entered its way into SolidWorks one way or another. Yeah.
Right. So yeah, so talk us through what are we gonna look at today, and where are you gonna take us?
Well, honestly, I mean, this SolidWorks live design may be more for me than it is for all of you, even though it is for all of you. But this is my kind of ode to mechanical watches, which is something that I got into pretty recently, within the last less than a year. By the way, I'm in a loud environment. You'll hear cars go by. Sorry.
Yeah, no worries. Oh, good.
It's something I got into within the last year, and it's just a really cool. I've always been into cars, right? Mm-hmm. And I live in Los Angeles, and we don't have ton of space here. So what I really wanted was a Survivor Porsche 912 to rebuild, but I didn't really have the space for that. So I kind of got into. I just found myself watching all these YouTube videos on people restoring and servicing old watches, and it just made me think about cars and how engines work, and it's like a little engine, and I got really excited. I mean, Steve, you and I were mechanical engineers. We get passionate and excited about mechanical devices, especially ones that are 100% purely mechanical. That makes me really excited. And I just kind of got into it. And if you're a mechanical engineer, you probably like tools. And when it comes to tools of the trade, the sky's the limit when it comes to watchmaking. There are literally thousands of different extremely specialized tools for little operations. And again, that kind of makes me kind of stoked, and I love it. So I thought, well, maybe I'll spend some time on SolidWorks Live Design and talk about what I've learned about watchmaking. And maybe I can get someone watching today not into this, but at least think that it's pretty cool or learn something new. I'm sure there are people on this feed who are like super watch nerds and probably know much more than I do. Again, I am a noob, but I thought it would be a good opportunity to share what I've learned in the last 6 months of just like playing around with a new hobby.
I'm super excited about it. I mean, especially when you're talking about the mechanical piece of it, especially when you start thinking about how long like watches have been around and these mechanisms that are involved and what they were accomplishing long before SolidWorks, right? I mean, so yeah, let's dive into it. Let's see.
For sure. Sure. Yeah, and that is another part of it that we'll talk about, is that how old these wrist watches are, and the level of machining precision that was done turn of the century is absolutely mind-blowing. Like, amazing. I still can't understand how they were able to achieve that level of precision. And like, when you have tolerance stack, like this is like the worst case scenario for tolerance stack up. And using, pen, some paper, maybe a slide rule,
right?
So I figured I'd start by just kind of showing like an image, right? So when we think of watches, right? So this is an Omega Speedmaster. This is like the holy grail for a lot of people who like mechanical watches. This would be like a dream watch for me, but
Okay.
I also kind of my wife's going to need a new car in the next couple of years. So I don't it's like the watch or the car is probably
Right.
I mean they are that valuable.
That's
But
crazy.
you look at this is called the movement. The movement is what is the guts of the watch, not the part you see. That's the dial in the hands. Now I'm starting from bottom floor and moving our way up.
Mm,
But I remember looking at images like this of like this movement and being like, it looks really cool. I have no idea what I'm looking at, but it
right.
looks really cool, and I like all the metal parts that there's cams and springs and gears, and that looks cool. But how does it work? And that really was and Steve, like I said, you and I are mechanical engineers. We can't just be like, oh yeah, I'm sure it's pretty complicated, and then just walk away from that. It's like, no,
Right.
I kind of have to figure it out. Like it's a personality flaw, to be honest. So I figured I'd start today by but stepping through like some of the guts of something that's part of every mechanical watch. So mechanical watch, they can range all the way from they just a two-hander, which would be just like hours, minutes. That's all that you see on the dial. And on
Hmm.
the other side of the spectrum, you have like chronographs, right, which
Okay.
have all these buttons. That you can use them for like a stopwatch and a timer.
Okay.
At the end
Right.
of the day, so all of those things that are added onto a watch that aren't strictly telling time, they're called complications. I'm sure you've heard that before, Steve.
Yeah. 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 It's
Yeah.
always an interesting term. Like I remember we were talking about Apple Watches. I
Yeah.
remember when they were like, "Hey, add your complications," and I'm like, "That's a strange term," but obviously it's rooted in some history, right? Related to watches.
Related to watches, and it kind of makes when you go through a watch and you think like, oh hey, I can add the date to this watch, I can add an automatic self-winding mechanism. They do complicate the mechanism quite a bit.
Fair
I don't
enough.
know the origin. I don't know the origin of the term, but everything on a watch is a complication. So those of you who are Apple Watch wearers, I'm sure you've gone through and it's probably the same with other sort of smartwatches too. It'll say, what complications do you want on your watch, on your face? And I remember being like, that's weird. So that's really where that term comes from. That's an old,
Okay.
very, very old term. So let's start by talking about, this is called the train of wheels, right? And all it is it's really just a gear reduction train. Or in this case, I think that the proper term here, Steve, would be a gear overdrive, because the
Okay.
power is coming from the largest or the slowest moving gear, and the output is the fastest moving gear. So I believe
Okay.
that the
All right.
correct term is called an overdrive, but I think that people tend to say a gear reduction for ones that go either way. So
Gotcha.
I'm going to flip this upside down. When we wind a watch, right now, I assume there are some younger folks probably on this call, but I think that we can all have heard of a watch that you wind.
Hmm.
Probably. What do you think, Steve?
Yeah,
You think that there are people
I think
like, what are
so.
you talking about? Winding a watch?
That's actually a good point. Let's
Like,
ask. Like, put in the comments. Have you used a watch that you have to wind?
or have you never even heard of that before? Like winding a watch, what does that even mean?
Right,
It's
right. Let's find
possible.
out from everybody.
Okay, so when we wind a watch, so this is a late '60s Omega, and I really like this company Omega. They make really really rad watches. So this
Mm,
is a this little crown. This is called the crown, the little wheel here. So when I wind it, what I'm doing is I'm charging up what's called the mainspring. This is the mainspring. So you can imagine it's a piece of like tempered, quenched spring steel, right? So
okay.
as you wind it, it's like whole tempering and quenching, right? You're trading like kind of like strength and lack of plasticity for brittleness a little bit, right? If you want to talk
Right,
about martensite and austenite, right?
right.
Some there's some probably some material nerds out there, but it's a little more brittle. But what it does is if you want, if the spring it'll deform, but it won't plastically deform, and you just basically you're filling this full of potential energy, right? So
Okay,
you're
got it.
winding, and you have all this stored energy here in this main spring here, and the barrel is going through this really simple train of wheels. This is just a pretty massive gear reduction. We have, I can go through. I have a little post-it note to remind me of all the numbers. So in this case, Um, right. This is a 400 to 1 gear step down. Right. Now remember, all this is fitting inside this little thing on my wrist, right? So these are teeny tiny little gears. So we have this pretty massive gear reduction. And what that allows us to do is wind a small amount, but let that, so a watch can power off that, just a simple wound spring for sometimes 2 or 3 days you can get out of this. Right?
Okay.
So,
Interesting.
So you get it's storing a pretty tremendous amount of power, more than you would expect. And when you open a watch up and you pull that mainspring out and it literally shoots across the room, you really do realize how much energy is being stored in that very small thing that's about this. It's about the size of a dime.
Okay.
And about 2 or 3 millimeters thick, really small.
Nice.
So on one side of the movement, now what I've done here is I've created this. This is a very simple view of the internals of a watch, where I've taken all the pieces. Now, we go back to this image, just like stacks on stacks of gears. So what I did is I took all the mechanical elements out and removed things like, these are called bridges. Those are things that kind of sandwich and stack on the watch, and just took all the mechanical components out so we can actually see what's going on. So on one side, you have a train of wheels and some stored energy in a spring.
Okay.
On the other side is really where the, whoops, didn't mean to do that, but I'll do it anyways. On the other side, we have what's called the escapement. And the escapement is back here. So the escapement this is where the brilliance of a watch really comes out. And this is when I saw how this worked, I was like, what genius came up with this idea? Right, so you have all this potential energy stored in the spring. And then on the other side, it's like, how do you take that energy and dole it out into packets, very small, regularly synced packets? How do you do that? How do you take the energy and let the energy leave the system in a very regular way?
Right.
And you do it using this escapement.
Okay.
So I'm just kind of moving over here.
The good thing is, Andrew, a big part of our audience actually have wound a watch. They worn a watch and that they've had to wind. So it's good.
I'm really interested. Has anyone said, I don't even know what you're talking about?
No. Well, we had about 30% that said that they had never worn a watch that they had to wind. But
okay, that's fine.
Yeah.
Okay, because that makes sense. All right. Okay. So let's talk a little bit about this escapement. Okay, so at the end of that gear train, at the very end, we have this thing called the escape wheel. Okay, it's funky shaped teeth. Now there's a reason for these funky shaped teeth. We have this thing, it's called pallet fork, and then we have what's called a balance wheel. Okay. Now in the balance wheel, this is the most important part of the watch, and someone could say, and this is called an impulse jewel. And let's kind of step through how this all works together in sync. So remember, there's 5 gears and a bunch of energy that really wants to turn this. It wants to turn so bad, Steve. So bad. Right? Really wants to turn. But this pallet fork says, you want to turn, but I'm going to stop you from turning. So this tooth is just jammed right against what we call the pallet jewel. And this angle is very, very important. Okay. So in this configuration, now the escapement wheel wants to turn, but the pallet is moved down and says, nope, you can't turn. But then because of this angle of attack, right, it's putting this motion, it's wanting to push the pallet jewel this way.
Okay.
Right?
Got it.
So the pallet jewel moves, so the pallet moves this way, and then you can see this little thing called an impulse jewel. It pushes that impulse jewel, right? It pushes it and it says, and then it stops here on what's called the banking pin. So this pallet fork can only move this far. Okay. But it's pushed on this impulse jewel, and it's made the balance wheel spin. Now, behind the balance wheel, we have something called the hairspring. This is connected to the chassis of the watch. So it spins a certain amount, but then it wants to spin back, right?
Okay.
It collides again with the fork, the pallet fork, and pushes the pallet fork this way, just in enough time for the escapement to move one tooth, but then it stops it again. Okay, it pushes it back.
Yep.
And then this whole process kind of goes, so the balance wheel moves, it pushes the pallet fork until it collides with the next tooth, and that is just repeated over and over and over again. Now on this watch, this happens 19,800 times per hour. Okay.
That
Okay,
is
so
nuts.
19,800 times per hour that happens, right?
Wow.
So we love SolidWorks. We use SolidWorks for everything. So of course we're going to use SolidWorks to kind of show this mechanism in action. So
Right.
hopefully my description made some sense here. So take a second to kind of look at this. I'll slow it down a little.
And Andrew,
So
maybe while we're watching this, what
yeah,
what did you use to create this animation?
so I use something called SolidWorks Motion, which is a rigid body dynamic solver, right? So if
Okay.
some of you guys may know about simulation or analysis, a lot of times people say simulation or analysis, we immediately think of FEA, finite element analysis, right?
Mm-hmm.
Or say I'm putting a couple loads on something like this pen and it's bending and I'm watching it bend on the computer and I'm understanding how much stress, is taking place and do I need to redesign? This is a different type of software where nothing is actually bending or deforming, but I can add motors and have parts collide with each other and have a transfer of momentum. I can add forces and springs and simulate a mechanical system, which is like a watch exactly. So
Right.
now we've seen how this escapement works, right? So the wheel pushes the pallet back, it gets hit by the balance wheel, and so this just goes on infinitely. Well, as long as there's pain, as long as there is power in the watch. So
Yep.
let's move to a different. So now let's see what happens when we kind of put it all together. Okay. So I told you between what's called the barrel, and this is the second wheel. This is third wheel. Again, real technical terms here, right?
Right.
So we have the barrel gear, which is also called first gear, the second wheel, third wheel, fourth wheel, and then the escapement wheel, which sometimes would be like the fifth wheel. That is now a gear reduction of 4,000 to 1, right? So
Wow.
pretty heavy gear reduction or over,
Yeah.
like we mentioned before. So let me go ahead and
Huh.
show this quick study, right? And it'll be easier when I show it from this view because you'll be able to see how all these gears are moving real slow. Probably can't see the barrel. Maybe if I speed it up maybe to like 10 times.
Yeah.
This is 10 times speed. We can kind of see the barrel moving a little bit. Maybe 1 pixel or 2 we see changing, right? So so this is moving at 10x speed. Let's go back to 5x. That was maybe a little choppy.
Andrew, that I've got a number of questions for you. I wanna encourage the audience though, if they have questions about any of this, please just put them in the chat.
Yeah.
I'm monitoring it. I would love to facilitate your question towards Andrew. So if you have questions, by all means, ask. But Andrew, one of the things that's just kind of realizing that
Uh-huh.
you haven't opened any like other assemblies, right? You're just like how did you facilitate, like I notice you're showing different parts and
Yeah.
you're flipping between some different things for maybe some of the people that are new to SolidWorks. Like what are
Sure.
the how are you accomplishing this?
Well, motion is pretty cool because if I hide and show parts, they
Hmm.
they are removed from the analysis, which is different than other sorts of analysis
Right.
software. So
Right.
if I hide them from my motion study, they are no longer part of the rigid body dynamics analysis.
Okay.
But if you look on the model side, I'm using something called display states, right? This is all one assembly,
Hmm.
but display states allows me to kind of set which parts are visible or not. Again, they're all being either hidden or shown, so
Okay.
they are all there. They're all there in the analysis. So when I turn anything, all of this stuff is goes backwards through the entire gear train. But display sets are a great way to kind of showcase like a pretty complicated assembly. Like, well, it's not that complicated. So look at train of wheels, and if I say train and escapement, let's look at that display state. And this is what I use as a starting point for all of these motion studies. Right.
And I have to imagine that motion must be. It's been a long time since I've used motion, but it's
Yes.
recognizing the mates, right? The mates that you've built into it. It actually is mate aware, I guess that you would say, right?
That's absolutely correct. It is mate aware. So, I mean, that could be another question. It's like, how do you get all these parts to move like this in SolidWorks? And I really like the gear mate. So lots of gear mates here, right? These are in the mechanical mates section. So if I open, say, one of these random ones, these are the mechanical mates. I'm sure many of you have seen all these standard mates, right? Concentric,
right?
Perpendicular, parallel. We've used these a million times. But there's all these other ones, right? There's these mechanical mates, which have cams and slots. There's rack and pinion, which is super helpful. These U-joints, that's pretty neat. And then some of these advanced mates, I'm kind of wondering, what is the advanced mates? Maybe you could teach me something. I don't really use advanced mates. Oh, right. So like symmetric. Right. We have width. It's funny that width would be an advanced mate. Profile center mate. What year did that come out, Steve? I'm pretty sure I remember.
Man, I don't remember. It all blends together after a while.
It does. But I think the profile center mate, I want to say that was 2013.
Yeah, you might be right. But it is funny that width is an advanced mate, because I use that mate all the time.
All the time. Do you ever use the trick, Steve, where you just control click all 4 elements and then it's there on the quick menu and all pops together?
Yeah, that's such a great tip for everybody. Yeah, if you've never used the width mate, if you want to center something up, just control select the 4 faces, bam.
That's right. Control select all 4, and then after you click the 4th one, take your hand off the mouse for a second, and a little dynamic toolbar comes up, and the little quick mate, you get the option to just click the width right there, and it all snaps together. It's much easier than going into the tool and choosing the tab and slot. I believe it's not even going to let me select that.
Yeah.
I believe it's the tab and slot is what it asks for. So yeah.
Real quick, while we're on this topic of these animations and the mates, we did have a question from 4D Modding. Asking how long did it take you to create this animation?
The animation? Oh, the animation is very, very simple. Well, it took a little bit of time. It was the timing that I needed to put together and make it all work correctly and make it look accurate. Now, I did kind of fudge this animation a bit because it'd be really difficult to actually make the system work the way it does, where I'm actually using the escapement wheel to push the pallet fork that then in turn turns the balance assembly.
Okay.
I don't. So what I kind of fudged it a little by actually everything is moving by defined motors using what I use. I like to use these segments. So in this case, I have the movement of the escape wheel is based on, and it should come up in just a moment here. Is based on this information, saying between 0 and 0.22 seconds, it's going to move 6 degrees one way and 6 the other. So I'm actually controlling the movement of the escape wheel using a series of segments between what time and what time. How many degrees is it going to turn from based on 0?
This screen alone, I think, is quite interesting, especially as an engineer, right? We all are like, ooh, graphs.
The graphs, yeah.
but I think it actually, it does a nice job, I think, because you immediately realize just how powerful motion is when it's like, oh my gosh, I can totally drive this motion based on functions that I, mathematically can define. So this is great.
Yeah, it's really cool. I remember when I first used motion, well over a decade ago, right? We have what we all learned in physics, right? Displacement, first derivative is velocity, second derivative of displacement is acceleration. Now, did you know that the third derivative of velocity is called jerk?
I did not.
It is called jerk, and it's a real thing.
Yeah.
I remember seeing that being like, jerk? Like, what are you calling a jerk? So, of course, you Google that and you're like, oh.
Yeah, it's a real thing.
So it's a real thing. It's called jerk. So this was not a lot of work. This was pretty simple. It was just kind of adding a few motors to control a few different things. I spent most of the time working on the timing so that I could, I hate to say it, kind of fake the effect. Now, can SolidWorks Motion actually create a working watch the way all the power coming from the barrel to move the escapement, and then all the collisions that take place between the jewels and the teeth of the escapement into the balance wheel turning. Absolutely. Much more difficult and not necessary as a visual learning tool.
Right.
If that makes sense.
Yeah, no, I mean, I think that totally makes sense. I think that's one of the things, right, about FEA and any kind of analysis is like, what's the goal, the outcome, what assumptions can I get away with and still accomplish what my desired outcome is? And like in this case, if it's simply to convey a learning element, assumptions are, as long as they're understood, are smart. So 2 quick questions, and then let's. Yeah. I definitely don't want to derail you too much. We have Aruna asking, what's the advice for SolidWorks beginners? I would say, a couple things. Just use the software. Just get in there, use it, join user groups. I think Andrew's going to show the tutorials are fantastic. These are all really great methods for getting in there and learning. And Avito wanted to know, can SolidWorks simulate the bending of those small hooks? And I think I know the answer to this, but I'm gonna let you kind of guide us on this one, Andrew.
Definitely not using the software though. Using our SolidWorks simulation FEA tool. Yep. If we could calculate the force that's going on between, say, this escapement wheel tooth and this pallet jewel, which we could probably get a pretty good understanding of what that force applied there, understand a bit of the momentum of the wheel. We could apply that in an FEA in finite element analysis and see how much that tooth is bending. Absolutely.
Okay.
We can even use FEA. We could use motion. Now, this is what I love for motion. If I were to set up the real physically correct motion analysis here, where I have all the springs from the gear train and actually collisions happening between the pallet jewels and the escapement teeth, I could solve for those reaction forces and then use that reaction force as my input as a boundary condition in a finite element analysis. So you can really start with a very small number of assumptions, only knowing how the mechanism works, and at the end of the day, getting real physics and engineering data that can help you make like a better design.
Gosh, I'm just always blown away and reminded like how much capability is available to us in these tools. It's crazy. So much
available to us. Okay, so let's move on. So that's cool. But let's go to a different display state. And now we should start seeing things that look a little bit recognizable, right? Yep. So now we have an hour hand, a minute hand, and a seconds hand. So this is where I think things get pretty exciting. So we can see actually how the mechanism works once we have like hands, and it kind of makes sense. Now, the people who originally, were engineers who designed these tools, it makes sense that taking one of these train of wheels, say, hey, that'd be convenient if one of these wheels was just seconds only, right? And that all has to do with when you're mapping out your gear reduction from between pinion and gear, pinion, gear, pinion, gear. It's like, if I can be real clever here with my math, and like I said, I have a little post-it note that tells me all the, that's backwards. Thanks, Skype. It'll tell you, all the gear reductions from gear to pinion. If I'm clever, then I can use one of them to help me out and give me, the seconds. This moves out in 1 revolution per minute. And one of them, like in this one, is the minute hand. So that's 1 revolution per hour. So those of you who have accomplished pretty low-level math would understand that, right, there is a 60-to-1 gear ratio between the second wheel and the fourth wheel, right? And it makes sense, which I think is pretty slick. Now, this would be an example of an older watch, right? Watchmakers call this like a sub-seconds watch, where you have where the second hand is below the hour and minute hand. That's sub-seconds, sub underneath. Now, this is an example of like an old World War II Bulova. I love the styling of a lot of these kind of World War II Army style watches. I think they really awesome looking. These were built to be 100% function, 0% fashion, and I think that's why I think they just look so cool. You know, typeset's so great. You know, I strap. Why do they call it that? What does that have to do with people in the military? And this is a NATO strap. If you can see how and the idea with the NATO strap is a good point, Steve. Is that if now behind this there's a little metal bar, right? So the NATO strap is designed that if either of these bars were to break or snap, the watch doesn't just fall right off your wrist, right? And that's so like if you look at this watch, if either of these break, watch is just going to fall right off. Whereas the NATO strap, um, it's right, like I said, one of them can break and it'll just dangle, but you won't lose your watch. So that's very functional. Has like 2 points of it's like a redundant system, which is pretty. Okay, so let's just take a look at the full assembly. I mean, I just like looking this for the eye candy. I think it looks pretty cool. But let's watch like the full assembly working. And this is what, so now we see kind of like the whole system kind of working together. It's pretty slick. So a pretty common question. I remember thinking this when I was first starting to get into watches. Like, oh, this is so cool. I'm understanding this like train of wheels and how the balance and escapement work. That's great. How does that work when you're trying to like change the time of a watch, right? So I don't know if my webcam's on, but right. So
Yeah.
I pull the crown here and I'm turning it, and well, I can control what the time is. So when I'm turning this, am I spinning all of those gears at like lightning breakneck speed? Like is the balance wheel going like that's crazy. How does that work?
That's
And
crazy. Yeah, that's a great point. It's like,
yeah,
how, yeah, I didn't even think about the fact that, yeah, how do you set the time?
how do you set the time? That's right. How do you set the time, and how do you not disrupt this very elegant, perfect little system? How do you set the time in there? And it's this is something that I mean, when I kind of discovered this and kind of learned about it, I was like, man, it's it's just an example of being extremely creative with design and engineering right, which we
Mm,
use a lot as engineers. Some people call it KISS, keep it simple, stupid. Some people just say that Occam's razor would be like the simplest solution tends to be the right one,
the right one,
right?
right?
Like so, it's it's an incredibly rudimentary clutch system that is just so perfectly mechanical. I absolutely love it. So, do you mind if I
Mm,
take a second and kind of discuss that?
yeah, let's do it.
So it all comes down to this part right here. This is called the cannon pinion. Let me just kind of zoom. So I'll just show this by itself. Ooh, don't want ambient occlusion on. So this is the cannon pinion, right? This connects to the minute wheel,
Yeah.
and it's got this notch in it. And we'll talk more about that in a second. So keep your mind on this kind of shape of this part.
Okay.
So I'm going to go ahead and just isolate these. Now, isolating is pretty cool that you can do in SolidWorks. If I select two parts and I right click and I hit isolate, it just hides everything else, right? So
Right.
now so here I have the minute hand, and it'll tell me, well, which parts are being shown, right? Everything's gone
Yep.
except a second wheel pinion, which becomes the minute hand
Yep.
pinion.
Yep.
Second, and this is second as in two, not second as in 1, 2, 3, 4, 5, 6 seconds. that's a funny homonym there
Right.
on a phone. Sorry, homonym, homonym. Uh, so I'm going to go ahead and use this. I'm going to split this thing, and we're going to kind of get a better understanding of what's going on inside here. And it's so simple, but so lovely. I just love this little system. So if I zoom in,
Yep.
oh, I zoomed in wrong. Let me go back here and let me rotate this a little bit. Yeah, rotate this section to like that. Perfect. So we saw this cannon pin. It's got a little notch on the side, and it goes pops in a little bit, and we can see there's a little teeny overlap, right?
Right. Little interference.
Little bit of interference, right? So the cannon pinion, you lubricate this air, it snaps on, right? You push it, it goes over this chamfer, and it snaps into this groove.
Okay.
And it's just the simplest clutch you've ever seen in your life, and it's about this big.
Okay.
And it's all about, right, kinetic friction versus static friction, right? So the static friction is pretty high, because if it had a very low static friction, your watch would be losing time all the time, because it would constantly, the cannon pinion would slip on the minute pinion.
Yeah, right.
So
Okay.
you'd lose time all the time. Or if it was too tight, right, you try to turn the hands and set your watch, and you'd be like struggling to turn it. So it's a perfectly tuned little clutch system that has one moving part.
Crazy.
And it's just, you tune it by changing the how big of a dent you're putting in the side of this part. And I kind of wanted to show this tool because it's like these simple little tools. This is a cannon pinion adjustment tool, and you see it looks like a wire cutter.
Right.
Flat side. So let me see if I can tile these windows so we can kind of explain this. And I'm sure everybody's already kind of well in the understanding of what's going on here. Not going to let me tile that. It's okay. Don't need to tile it. I can just flip back and forth. So we have the sharp part of the tool pushed into the groove. Sorry. And then you use just like this little wheel on the side to kind of slowly push the sharp part into that groove and give it push it a little more. And like it's pretty obvious when a cannon pinion is loose, because your watch is losing time, but then you put it on something called a timegrapher, which listens to the clicks of the watch, and it tells you how accurate. So you put the watch on the timegrapher, and it says your watch is losing 2 seconds a day, which is like nothing. But then you look at the watch and it's losing 10 minutes a day. It's like, okay, I've diagnosed it pretty quick that the cannon pinion is too loose. And cannon pinion too tight would mean, like, obviously, right, it's hard you can't actually set the time. So you use something like a little teeny smoothing broach, and you get in there and you just kind of shave like maybe 800 atoms of a very small amount of material you remove until the cannon pinion clicks on. You push it and it just goes, and it's got this perfect, very satisfying little snap, and you got it right.
Nice.
So the cannon pinion is kind of like the unsung hero of like watch design, in my opinion. It's it allows these two systems to work together, the one that you see and the one that's going on in the background.
You gotta imagine, like, whoever came up with this, like, just that completely satisfying moment where, like, you develop this super simple solution that just has this amazing impact on the overall design of what's happened. I think as like engineers, that's just super satisfying when you can engineer complexity out of something and still achieve an end goal, right?
Totally. But sometimes, Steve, do you ever like kind of want to see all the failed attempts at doing that? It's like, I'm sure there were like all these weird tools that had like plates stacked on top of one another with like some sort of friction plate, like in a clutch of a car, like all these things. And someone's like, what if we just like put a little notch in like this little, in the little cog here, and it just, you can move it. You just got to give it a little bit of oomph. Yeah. You got to just, it has to be perfect. So the cannon pinion.
One thing I did notice real quick, can you isolate a couple parts again, or
sure.
Isolate those two parts?
Those two.
Something I want to point out for everybody that I find very handy at times is when you isolate, you can you'll notice on the isolate dialog that pops up, you can save that, right? So So if you've got a complex machine design or whatever, and you go to the effort to find the parts that you want to isolate, you can save that as a display state, which is super handy.
Super handy. Yeah. It is really handy. I mean, I use isolate all the time. I really do. There's also, if you don't like I mean, not if you don't like isolate, but we always have a few different ways to skin the cat, right?
Yeah.
So we can click these two, and also if you right click and select, where are you, component preview window, right?
Yeah.
Now I can look at those parts by themselves in their own little window without disrupting. So it's just another way of doing kind of the same thing, and we can see everything kind of at once.
Yep.
I love the component preview window. Okay, so let's because we're in class and we're learning. So I wanted to show this because we should be able to, hopefully, if I've done my job even a little bit correct, we kind of have an understanding of what we see here, right?
Yeah.
So this would be like kind of like a skeleton watch movement, but where you can see everything, right? We've got our barrel, and we've got our barrel gear, which is, the barrel gear is just the teeth that you see right on the edge here, right? We have our gear train, so we have our gear train going from barrel to second gear, which in this case is also the center, right? Remember, we saw that that center pivot is also the minute hand. Yep. And then we have our reduction here. We have our third wheel. Fourth wheel, if we zoom in, we can see, it's hard to see, but there's a little knob on the end of that thing. And that knob is where our seconds hand connects. This is a sub-seconds watch. And then we have our balance wheel and our pallet fork and our escapement. Now, what we haven't talked about is what's on the other side. So this is called the dial. This is the balance side. And then if you flip it over, this is called this is the dial side. So this is where we would, all the mechanisms and springs that we'd use to wind the watch, right? So this winding mechanism, it's really simple. This winding mechanism is this gear actually this is the end of that gear here. That makes sense?
Okay.
So when we turn that gear, we turn this thing called the crown wheel. Crown wheel turns this thing called the ratchet wheel, and then this click is basically a little ratchet, and that charges up the spring, right? So that's the interface. And then when we pull the crown in and out, and we snap from this, it goes from this well to this well through a couple different levers. And then it pushes this thing called the name escapes me, but this is how it basically pushes this across the actual arm, and then that's how we actually set the watch.
Okay.
So yeah, pretty slick. So we can kind of see here, it's kind of hopefully a little bit demystified, not like you guys may have thought of it. One thing I forgot to mention, right, is how the hour hand and minute hand work together. I did forget to mention that. We have just another, this is essentially a 12-to-1 gear ratio here between this is this guy here. This just takes the minute hand and reduces it by 12 times, and then over this sleeve which runs the hour. So the hour and the minute hand are everything's connected, but it's all based on the minute hand powers the hour hand, not the other way around.
Gotcha. Hey, one question that maybe is a good time to ask, going back to kind of the motion. We had another question that said, if you animate add motion, is it possible to export the positional coordinates in XML? So, for example,
positional coordinates in XML?
Yeah, I can animate a machine that has 3 axes and spit out the XYZ for use in other software.
Let's try. So we'll make a plot here, yes, you absolutely can do that. So if I look at the displacement, I want the linear displacement of this point right here. Okay, I want to see how this thing moves through 3D space. Okay, I can say okay. Ooh, what's it doing? Result component, of course. I want it to see how it moves along the z-axis. Okay, it's good. Why are you not telling me? Why are you not giving me my result? It wants it in relation to what? So how about in relation to this? No, why aren't you working? Boy, I thought that I was like, hey, yeah, sure, I got this. Let's see.
Yeah, no worries.
Let me see. Should be able to understand. the displacement. Yes, the displacement of, I mean, because it isn't, we'll look at angular displacement, probably because this is based on this part. Let's see if I get a result here. There we go. So it's kind of, it's kind of all over the place, right?
Sure.
So I can now, if I right click in here, let's see, where can I export as CSV, right? So I can export
Okay.
this plot information as CSV. Now I'd have to export the X, the Y, and the Z separately, but in Excel it'd be easy just to line them up because you just grab the XYZ coordinates, put them into a plot, and you can get the XYZ output of everything in an Excel file. And does that answer the question, you think?
I think so.
It's not perfect, but
Yeah, it's
it's
not.
close.
Yeah, but I think it probably gets them in the right, headed in the right direction. You know what? I think again, I know the answer to this, but where someone was asking, or is the motion study accurate? And unlike just a normal animation you might do in a 3D software, this is in fact taking into account physics and friction
Absolutely,
and all of
100%.
that.
Yes. This is a physically accurate software, but what we like to say as analysts is your output is only as accurate as your input, right?
Right.
So how accurate are you when you are defining things like spring rates and spring damping, right?
Yeah.
Those can be difficult things to just pull out of thin air,
Right. How
right?
well do you understand the assumptions that
How well do
you're making as well, right?
Absolutely. If you know if your assumptions are accurate, you will get accurate results. If
Yeah.
your assumptions aren't accurate, yeah, you can. I mean, sometimes engineers also use a different term. They say crap in, crap out. So that's another term.
Fair enough.
Fair. Okay, so I'm changing gears a little bit, and that's a terrible pun. I apologize. It was not planned. Um, but I'm going to change my webcam here because I have a little microscope that I've set up.
Okay.
Hopefully you can see this little microscope. So I have a microscope that I 3D printed a little mount, and this is the latest watch I'm working on. This is the brand is called Enicar. This is an Enicar 11-20-25 movement, and I literally 2 days ago I finally got this thing to tick.
Okay.
So again, we can see all the main components. Let's kind of
All
move
right.
over
So
here.
this, Andrew, this isn't a video, right? This is
Oh no,
you.
this is me. See, I can wave with my finger.
All right. All right. Very cool.
No, this is not a video. Um, we can see, let's see, below this gear, boy, I wish you'd zoom out a little bit. That is, we have our barrel
Yeah.
and our center wheel, which is also called the second wheel. Third wheel is below this bridge. Fourth wheel is behind there. We see our little escapement moving. Let me get that in focus. We see our
Yeah.
escapement and our pallet fork kind of just hammering away in there, and then our
Yeah.
balance. Now, you know how like when you look at like a fire burning, sometimes you find yourself just like staring at a fire burning, like for like, and you're like
Right.
nothing's happening, but you're really mesmerized by
Right.
fire burning. I find the same thing. Look at a watch movement and like watching that hairspring like growing and what appears to be growing and shrinking. I just think it looks
Yeah.
so cool. It's really it's awesome. I'm gonna remove movement from my little holder here and flip it around so we can see again the unsung hero of watchmaking here, which is, where are you?
Andrew,
That.
I think you'll be happy to know. I think there's some fellow aficionados. You've got a
Oh,
Someone's asking, have you ever looked into the Resonance Type 3 liquid filled watch?
I can say categorically the answer is no.
Okay.
Haven't haven't looked at that. It sounds very gnarly though. No, it sounds cool. What's it? Category three liquid filled movement?
Yeah, into the it's the looked into the Resonance Type 3 liquid filled watch.
I wonder if it's like a fluid drive.
Yeah.
Interesting. I
Yeah,
will look
yeah.
at. This is our Canon pinion right here.
Oh, okay. Got it.
That's our Canon pinion right there. And now this is a center seconds watch, so you can't really see it, but there's a little pinion in the middle there. I mean, you can barely see it just moving very slowly, but that's the seconds hand. The seconds hand will connect to that.
Okay.
So I'm kind of jumping all over the place here a little bit now,
No,
but
that's
the
all right.
last
It's
thing
cool.
The last thing I wanted to share was, which is a pretty. Oh, I should at least keep. Ah, okay. Let me change my.
You okay? You all right?
Yeah, look, everything's falling. It's all fake. It's all hanging up hanging on a shoestring.
Right.
Let me change back to this. Okay. So the original charge of me wanting to do this live design was based on this thing right here. I know I don't want to take too much time here, but this is called a timegrapher. I mentioned this a little bit earlier. Now, if you've ever gone to a watchmaker, they put your watch on this thing, and then somehow, some way, it tells me how many, in this case, how many seconds per day. This is saying this is gaining 30 seconds a day. Okay. This next one, amplitude. So you saw the balance wheel spinning, right?
Yeah. Yeah.
This is saying that the entire rotational path of the balance wheel is moving 216 degrees. Okay.
Interesting. Okay.
So that would be like 108 in one direction, and then that impulse pin hits the pallet fork and then
Yep.
moves 108 the other way based on this. We have this thing called a beat error, right? This one's pretty easy to understand. So, right, we have 108 on each side. If that was the case, our beat error would be 0. Now, say it was doing like 100 on one side and 116 on the other, right? So it's kind of like the balance wheel isn't perfectly. The timing between when it hits and then when the pallet fork moves and then pushes it, it's the angle between that motion. Okay, now that's kind of like an intrinsic property of a watch, but it's pretty interesting. So I wanted one of these because I want to be able to tune my watches and get them all, dialed in right. But I looked into what this is. All this is this is just a microphone. That's it. It's just a microphone.
Okay.
And it can get all of this information comes just from hearing the tick tock of your watch. It can discover all of this information, which is pretty cool. And this one is the one that kind of blew my mind. How does it know how far the wheel turns?
Right.
If we have time, I can talk about that. It's, again, you get a bunch of smart people in the room, and the sky's the limit with what people can figure out. So I found a piece of software a free piece of freeware that can actually do all the calculations that a timegrapher can. So I decided to design and 3D print a little mount so I can mount my watches. And this is what it looks like. And I mounted it on this microphone here.
Oh yeah, look at that.
And most of them have like a series of springs and slides, and it's kind of complicated. I wanted to make this as simple as possible. So I was like, what if I just use a rubber band? I want to somehow design this so a rubber band can be what keeps the movement pushed onto the top of the microphone piece. Okay. So if there's time, I'd be happy. I could kind of step you through the design process of that because it was kind of fun. And I really, really enjoy.
Hey, real quick, Andrew, that last parameter, because I think we had a little bit of an issue with the audio. That last parameter you said was the angle that the escape is moving back and forth. What the 52-degree parameter?
Yeah, let me talk about that again. Okay, so 52-degree parameter, this one here. So if you remember our pallet fork and the impulse jewel. Right?
Oh, okay, got it. Yeah.
Right. So the pallet fork can move like this, and the impulse. So it's the degree of it's like if you were to take a straight line from the pallet fork this way, and it's when that impulse jewel hits the front end of the fork, and then it's pushing the fork, and then at some point the fork pushes the balance jewel, right? Yeah. And it's when that finally releases. You take that angle. So the angle from the release of the impulse jewel to the initial touch of the impulse jewel. Yep. And it's that timing that can actually tell. I mean, I'm kind of getting into a place I shouldn't be because I'm kind of going a little off the rails here. But if you look at this, tells you how the timegrapher can actually understand that amplitude. Yeah. Based on the timing of the click of these two taps. I mean, it's really very, very small. Imagine if if the slower that is,
Yeah.
means it's really slugging along. The faster it
Okay.
is, it's moving much faster. And you can
Right.
see
Okay.
this really simple curve here that can tell you, based on those, the two hits, it'll tell
Huh.
you what the amplitude is. Okay.
Got it.
So
Thanks.
yeah. So now I'm going to just step through a little bit of this timegrapher mount. Pretty simple design, but I like designing multi-bodies when I'm doing something like this. I always find it a lot easier to design because, you know, I can build all my parts as I find it much easier to build things like tolerance in, right? Like I know exactly that um, this pivot off of this arm, I wanted exactly like 0.3 millimeters of gap, right? Because I want to be able to fit it because I understand with my 3D printer what the tolerance is of the
Sure.
print. So I want to make sure that it's going to fit. And doing this all as a multi-body part makes it much, much easier to create all these parts that I know are going to fit. There's zero, I know that all the interactions are correct. There's absolutely no interference because I can check that. And then I can save those bodies out later and create individual parts from them.
Okay. So maybe just to back up a minute. So you've got a single part file. Maybe we've got a few people that are kind of new to this. So we've got a single part file,
mm-hmm.
but effectively, instead of like when you did an extrude or whatever, you just uncheck the merge result. We're not doing a Boolean operation anymore. We're just allowing that body to basically live on its own as an entity.
That's right.
Is that fair?
That is absolutely fair. So
okay.
So I'm going to step through a couple things here. Maybe I'll spend just a couple seconds of like kind of how I started. So the original sketch, I like to do this. I took a photograph of my microphone, and I like to take a photograph with the measurement of my calipers all in one. That means I know exactly that this distance is 28.7 millimeters. It says it right there.
Gosh, that's a great idea. Yeah.
So I never have to like write something down. It's like all this one image says absolutely everything I need. I know exactly that distance, so then I can just build my sketch along, like that.
Mm-hmm.
And, I hid that body, so I should show it. So the first thing I did was I just designed the microphone. Oops. I designed the microphone,
mm-hmm.
and I added this I thought was clever. I added a split line of where all of these, if you can see on this mic, I have some switches here. I have like a microphone jack. I have a couple things here that I knew I didn't want to design over those areas. Those are like keep out areas, if you will, if you're like a PCB designer.
Sure.
So I designed some keep out. I just put a split line, which is really simple. You just created just a line, just a sketch, right? I knew exactly what that distance was from this lip. It's 9.62 millimeters. And then a split line, what it does is this tool, I can project that line and cut the part and create new faces. You're creating just faces with that split line. So I knew as I was designing, this is my keep out zone. I can design up to this line, but no further than that line. And I even put a tolerance on that 9.62.
Yeah, that's smart.
And this is just really, so I want to I'll show my first multi-body command here. So that's down, let's see, which one was it? Here. So here I designed a separate body, right? So this kind of little lever is a different body than the main housing.
Okay.
And this one. So just like what you said, Steve, if you deselect merge result, right, it now lives as its own body. Okay. And every other extrude command after that, it's going to ask me, well, you created an extrusion here. Do you want to add that to an existing body? Do you want to create your own new body? So I selected the new body that I created here because I didn't merge it. And I said, I want this new post to be added to this body, not this one, and not to be on its own.
Oh, right. So you can selectively choose where you want the addition to happen, basically.
Exactly.
Okay.
And like I mentioned before, the reason why I chose multi-body here is specifically for which one of these sketches, this one. Like this sketch, there's a lot going on here. This says, right, I've converted the entities, meaning I grabbed a sketch from this existing geometry, but I knew I wanted 0.15 radial gap between that post and the hole, because I know that that's about the limit of tolerance of my 3D printer, because I want to make sure that it fits.
Okay.
You know, and this kind of stuff I think is very easy to do on the fly when you're doing it all in a part as opposed to an assembly. Really, like I said, multiple ways to skin a cat. I mean it. I'm sure there's people out there just wanting to punch their computer saying, why would you ever do it this way? This way is way better. And your way, I'm telling you right now, your way probably is better than mine. I am not the super master modeler of folks like Jordan Tadich out there who can super master modeler. But I just wanted to show that you can, by using the save bodies command, pretty neat, I can say, okay, it has all these bodies, but I want them to be individual parts as well, because I'm going to build an assembly from this, because I want to look at how it moves and make sure that it behaves the way I expect it. Because in a multi-body part, I can't like grab this arm and move it around like I could mated parts in an assembly. Right. So I saved these bodies out, and then I created a very simple assembly.
Hey, real quick, I want to just say we are at the top of the hour. Thank you guys for hanging with us. Obviously, I think Andrew's got a few more things to show. If you can continue to hang with us, that's great. Otherwise, thanks for joining us. But Andrew, I think you've got just a couple more things, right? This
is the last thing, and then I want to actually show the timegrapher working, which will be about a minute or two. Yeah. So this is just a simple assembly where I've now created all the mates so I can actually monitor and make sure that, this is why I built these stops, to make sure that it doesn't clash when it hits. Really simple. And I even have a little cutout for my rubber band. Thank you.
So this is interesting because it's almost like the best of both worlds, right? You get the whole sense of building this thing as a single entity, if you will, but then from what I'm seeing, you can export it as the assembly and manage your motion and do your, those types of things. So I guess my next question is if you make a change to that original part, does the assembly, everything in the assembly update?
You just have to rebuild. Yep.
Okay.
It says, like if you look at any one of these parts, I don't have a bunch of features. It just says, hey, this information is coming from the timegrapher mount part. So as that part changes, so does this.
Okay. Gosh, there's so many implications for this in like plastic design and other areas that I know we could probably spend a whole show on, but
I mean, and it's very useful when you're trying to design something based around an unfinished design.
Right.
Right. Like you can kind of get work done, but you're like, I know this thing isn't finished yet, but I can start working on it. And then when that's finished, you can swap out the base part and everything will just build around it.
Sure.
Right. Because you've used it. So this will be the last thing I show. Sorry for taking too long. I get too excited about this stuff. So this is this piece of software that I found. And let's see if I can get it to actually. So I have my Omega watch here that I have.
Yep.
And it's on the timegrapher. It seems like it's not coming through yet. Let's see. Why are you not working? Always the case, right? So, but when it does work, it's cool. Let's see if maybe I just need to restart. Start it up again. And if it doesn't work, it doesn't work. No big deal. But it's pretty slick to see this software working.
Because this is something you said you found for basically it's open source or it's
it's free software that you can just use as you need. Let's see, is that working? Let's see if my mic's working. Yeah, maybe this doesn't work this time. Could be something to do with the call that we're on.
Oh, sure.
But, yeah, normally this works. But it would show that this watch is a few seconds fast.
Okay.
And, oh no, this would have been pretty cool. But not working. Okay, anywho.
All good.
Thank you all for letting me waste over an hour of your time talking about a passion of mine.
Oh, yeah, not a waste at all. I think that's the fascinating thing is you find, things that maybe aren't your hobby, but you find somebody who's passionate about it, and then you mix it with something that you kind of are passionate about, like SolidWorks, and suddenly it's, an hour goes by and it's been just a tremendous amount of fun. So to everyone that's still on the call, thank you for sticking with us. Andrew, thanks for all the effort to go into this. I learned a ton. It was absolutely fascinating, all of the both the SolidWorks side and just the history and what's involved in watchmaking. If you have a chance, we have a couple more events coming up on 8/25. There's another live design where we're going to be looking at data management topics. On the 26th, it's going to be another live design, and Sean is going to be walking through aspects of the API for designers, so you won't want to miss that one. And then as we look forward to September, we've got the Slug Me event, the largest user group meeting, which happened last year, doing again this year. Just an absolutely phenomenal marathon of an event, so much fun. And then everybody's favorite, What's New, is going to be part of our live lineup as well. So make sure you're part of those. Like, subscribe, get notified, all that good stuff, because you're gonna love it. We've got just some great content coming up over the next couple of weeks. So with that, Andrew, again, thanks for joining us.
Thank you so much, Steve.
Yeah.
And thank you, Jesse, in the background. He's in the background.
Yeah. Big shout out to Jesse and Ian producing this. They always make Andrew and I look good, and we're able to just focus on a great conversation. So with that, enjoy the rest of your day, and we'll see you again soon.